So, welcome back. Today we're going to be looking at first order linear ordinary differential equations. So, first order linear ODEs. Linear ODE. Okay, so let's consider this. dy dx plus p of x times y equals q of x. So this is always what we want to strive to get towards. We always want to try to get all of our questions in this form. So typically we get questions like fx times dy dx plus some arbitrary function of x times y plus that's equal to another arbitrary function, which is u of x. So typically what we got to do is divide both sides by the multiplicative inverse. So we got to say 1 over f of x. 1 over f of x. So everything is in the form of dy dx. Basically in this form, right? Before we get to doing some problems, practice problems, I want to figure out, I want to show you guys how to derive the form that we require to solve this, which is basically just this, the formula to solve this, which is being written right now, times q of x. So I'm going to show you guys how to derive this, because I always think that it's good to know how to derive things so that you remember it better. So I'll just be really quick. If you want to skip this, you most certainly can. So let's see. The first thing I said, we always have to remember this. Q of x. Always got to remember this. So just consider this. Don't ask me where this comes from. I'm not really sure. But hey, why not take the derivative of it? That'd be pretty interesting, right? So in order to take the derivative of this, we have to first break down what this is. So we know that this is two functions being multiplied to each other. So we immediately know that we can use the product rule, because y of x, a function, is being multiplied to e to the integral p of x dx, which in itself is another function. Say this is like f of x times g of x, which is what this whole thing is. So let's just revisit the rule for the product rule. So that's going to be u of x times v of x. So that's just going to be u times v prime plus v times u prime. So in this case, let's just say u equals y and v equals, actually let me use a different color. Let me use yellow. Okay, so u equals to y and v equals to e to the integral p of x dx, right? So we know u prime is equal to dy dx. We know that v prime is equal to p of x times e to the integral p of x times d of x. Why is this the case? Well, we know that the derivative of exponential functions to the base e is equal to this in itself, the function that we're taking the derivative of, multiplied to the derivative of the power, which in this case is the integral p of x dx. So taking the derivative of this, we know that the integral and the derivative cancel out. That just gives us p of x, which is just multiplied over here. So what is this equal to? Let me get another page to write this. So u equals to, let me see, u equals to y, v equals to e to integral p of x dx u prime equals dy dx v prime equals to p of x e to the integral p of x dx. So again, the derivative of this, so let's e to the integral p of x dx. So the derivative of this is going to be u times v prime plus v times u prime. Let's see, is this correct? U times v prime v, so that's e to the integral p of x dx times u prime, which is dy8 dx. Now that we have this, we notice that the integrating factor is common for both sides, for both parts of this right hand side, so like we can factor it out basically. So this is what it's going to look like. This is equal to y times p of x plus dy dx. So remember what I said before, y times p of x plus dy dx equals q of x. Well, now we can bring that and use this substitution over here. So that's just going to be d dx y e to the integral p of x dx. And that is equal to just the integrating factor times q of x. And that's where we, there's one more bit, not there yet. So if we take the integral both sides, dx, take the integral of this side as well, we know that the derivative of the integral cancel out, so we have y times e to the integral p of x dx equals to the integral of the integrating factor times q of x dx. And that's where this comes from. Now we will try a practice problem. Let me get a different color for this. Let's go with orange. So we have 3x times dy dx plus 9x cubed plus times y. So 9x cubed times y, and that is equal to 18x cubed. So we have to get everything in the form that we want to, which is with dy dx without any coefficient. So let's just divide both sides. Okay, let me just show that. Sorry. So we can multiply both sides by the multiplicative inverse of the coefficient of dy dx, which is 3x dy dx plus 9x cubed times y. And do the same for the right hand side. And this is just going to equal dy dx plus 3x squared times y. And that's going to be equal to 6x squared. So what we can do now is we can say that p of x equals to 3x squared, q of x equals 6x squared, because that's what the original form dictated. So we can just make those substitutions. So this is p of x, that's just q of x, right? Because dy dx plus p of x times y equals q of x. That's why. So now let's cordon this off. Choose a different color for this, which is green. we know that y e to the integral of p of x dx equals to the integral of the integrating factor times q of x dx, right? So y times e to the integral of 3x squared dx equals to the integral of e to the integral of 3x squared dx. That really rolls off your tongue, doesn't it? And that's times 6x squared. So satisfying to say, but anyways, what we do now is we considered this power integral separately, so that's just going to be 3x squared dx, and this is pretty self-explanatory, I think. This is going to be x cubed, because 3x cubed divided by 3 is equal to just x cubed. We're going to ignore the plus c for now, because we're just assuming that everything, like the constants of integration, is just added up, so we're just going to ignore them for right now. So let's go on to another layer. Y e to the integral 3x squared dx equals to the integral of e to the integral of 3x squared dx times, what is q of x again? 6x squared. So as we said before, this is just going to equal y e to the x cubed equals the integral of e to the x cubed times 6x squared dx. So you immediately notice that there's some sort of relationship between x cubed and 6x squared. And what I notice is that if you take the derivative of x cubed, that's just going to be 3x squared, right? And 3x squared times 2 is equal to 6x squared. So that provides us a basis for a u substitution, which is what I'm going to do right now. So I'm going to say u equals to x cubed du equals to 3x squared. And that is basically going to make us say that integral of e to the u du times 2. Now we think times 2 because if you see du, that's just equal to 3x squared. In order for it to be equal to 6x squared, we have to multiply du times 2. So that 2 will just go outside the integral sign. It's just going to be multiplied to the whole integral. So now we can say 2 times e to the u, because the integral of e to the u is just going to be e to the u, equals to y e to the x cubed. So this is equal to that, right? Let me just rewrite that. Doesn't look that great. I think that's slightly better. This is not an x, by the way. This is a dot. So let's make the substitution again. So let's write this in terms of x equals to 2 e to the, also by the way we have to say plus c over here. Now we can put the plus c. So 2 e to the x cubed plus c. Divide both sides by e to the x cubed. You get y equals 2 because, okay, let me just show that. E to the negative x cubed. E to the negative x cubed. So negative x cubed here cancel out. So you're just going to be left with 2 plus c e to the negative x cubed. And there you have it. That is first order linear ordinary differential equations. If you have any questions, leave them in the comments, and thanks for watching. See you in the next one.